Alright, hi everyone. Last time we were talking about the inverse trigonometric functions, and specifically we were focused on the first example of an inverse trig function, which was the inverse of sine. So remember, sine inverse x was the inverse of the sine function. And sometimes instead of writing sine inverse like this, you also write this thing. Arc, A-R-C, like the English letter arc sine x. Okay, so there's a very minute difference between sine inverse and arc sine, but in this class they're essentially the same thing. So these guys are equal. And remember, we said that sine inverse has domain -1 to 1. So sticking to like the paradigm of trig functions that you learned, in trigonometry, you can think of these as like lengths or displacements. So normally a trig function takes in an angle and gives you a ratio of lengths or displacements. In this case, the inverse trig function takes in lengths and then it spits out angles. So the range is going to be -π/2 to +π/2. And remember, the reason why we did this is because normally sine is not 1 to 1. Like if you look at it from -2π up to +2π, it fails the horizontal line test very badly. This is sine x. It fails the horizontal line test pretty badly. So it's not 1 to 1, meaning we can't find its inverse. But if you restricted it between -π/2 and +π/2, where it takes on the value -1 and +1, then on this little branch here, this blue arc, it was 1 to 1. And so this is why we restricted the domain of the original sine function to be this, and so the range of the inverse function is that. Because remember, domain and range flip-flop between the inverse and the original function. Okay, and then we did one example, so let's do another. Let's find the tangent of, now let's call it arc sine of 1/3. Not 1/3, yes, 1/3. Okay, so say we want to find this. And again, this makes sense because this thing here, you can think of it as an angle. The arc sine function takes in a length and then it spits out an angle. And so we can take the tangent of that angle. Now, the fact that arc sine of 1/3 equals theta, let's explore that a little more. So arc sine of 1/3 equals theta. Now again, remember that anytime we have an expression like this, we can rewrite it as the sine of theta is equal to 1/3. And this is using the fact that, remember, if we had f inverse of y equals x, this was equivalent to f of x equals y. And then remember, with another way of thinking about this is with our little blob diagrams, is that 1/3 here, this is in the range of sine x. And then this is the domain of sine x. So we took something from the range of sine x, which is actually the domain of sine inverse. So So this is the domain of arc sine x, and this is the range of arc sine. So we took something here. So you stick 1/3 into the arcsine function, and then that's going to be some angle theta. So when you stick this into arcsine, you get some angle theta. Meaning that if you want to go the other way, that the sine, if you apply sine, so stick theta into sine, that gets you back to 1/3. And that's why these two are equivalent, and that's essentially what this is saying, except this is in the specific context of sine and cosine. I'm sorry, sine and sine inverse. So now that we have this established, we can basically draw a triangle out of this. So what we're saying is that this arcsine 1/3, it's some angle theta, okay? So I'm going to draw a right triangle and call this theta. And what I know about the sine of this angle is that it's 1/3, meaning that the opposite length is 1 and the hypotenuse is 3. Okay, and then if you use the Pythagorean theorem, you can see that 3 squared must be equal to 1 squared plus, let's call this x for now, x squared. So then 9 is 1 plus x squared. So x is the square root of 8. So this is root 8. Okay, so then what the problem is essentially asking you to find at this point is you want to know the tangent of this angle theta. Well, now we can just read this off our triangle. The tangent is the opposite divided by the adjacent. So this is 1 over root 8. And that's the answer. So this really complicated looking thing really is just 1 over root 8. Okay. And then now let's get into the calculus part of stuff. So what is the derivative of sine inverse? That's the first key question. And to answer that, we can basically use that formula that we had, is that f inverse prime of x is 1 over f prime of f inverse x. We're going to use this formula to answer that. So what this means is that sine inverse prime of x, so the derivative of sine inverse, should be 1 over, now the original function f of x is sine x. So what is f prime of x? The function here, f prime x, is going to be cosine x. So let's just keep that in mind for a second, but we'll write this as f prime of f inverse of x. And in this case, we'll write sine inverse. And actually, let's just do this. So f prime becomes cosine. So inside of the cosine function, we're sticking this guy, which is sine inverse. So that's what this becomes in our particular example. So stick the inverse function, sine inverse, into the derivative of the original function, which is cosine. And now again, we can turn this into a picture, because this guy is going to be an angle. Remember, x is some length, and when you take sine inverse of it, it gives you an angle. So we know that we get this triangle, where if I label this angle theta, then what do I know? So we just said that the sine inverse of x is equal to this angle theta. And this triangle doesn't look like quite a right triangle. Let me redraw this. There we go. So this is now theta. We said that sine inverse of x is theta. And so remember, using the little trick that we've been doing a lot now, we now know that sine of theta should be equal to x. These two are equivalent statements. Meaning now that I'm going to rewrite this a little more suggestively, is that sine of theta is x divided by 1. Meaning that if you look at this triangle, the opposite length is x and the hypotenuse is 1. Because the sine of this angle should be x divided by 1. And then again, if you use the Pythagorean theorem, you would get that this is the square root of 1 minus x squared. If you have questions about this, feel free to ask me in class, but that's what you're going to get. And so sine inverse, the derivative of sine inverse is just 1 over the cosine of this angle theta now, which we can just read off of this right triangle. Okay, what is the cosine of this angle? Well, it's this adjacent divided by this hypotenuse, but that's just anything divided by 1 is itself, because it's going to be adjacent over hypotenuse, which is just itself. So the cosine of theta is this. So we just get 1 over the square root of 1 minus x squared. And now we've actually derived the derivative of inverse sine. Very cool. So we now have the derivative of the inverse sine function. That's pretty neat. It looks very, not too bad, right? It seems kind of random too, but this is what it is. Just looking at how we built this, it has to be that. And so we can do this for the other trig functions as well, and their inverses, but for a second, let's look at an example here. Just to really solidify what we just did. So basically, we now know that d dx, the derivative of the inverse sine function, is this. That's now another formula here. And then remember, you can only stick numbers between 1 and -1 into this guy anyways. But if you stick 1 or -1 into here, you'll be dividing by 0 because you'll get 1 minus 1. So the condition here now is that you can't include -1 and 1 here. So this is true for all those. Okay, and so now what if it wants, suppose you want to find the derivative of this. Of x squared minus 1. Say you want to find the derivative of this function. Okay, so according to this rule here, our x in this case is all of this. So we're going to again use the chain rule. So we cover this up and we say, according to our derivative rule or formula, this is 1 over the square root of 1 minus the thing we covered up. So 1 minus the quantity, x squared minus 1. That's what like x is in this case. This here is actually this in our problem. So this x gets replaced with that. And now I see that I should square this as well. So it's this guy. So it's 1 over the square root of 1 minus the thing we covered up squared. But then, because of the chain rule, the price we pay always is we have to multiply by the derivative of what we covered up. So multiply by the derivative of that. Okay, and then I don't know if the problem wants us to simplify this. Okay, yes, it simplifies it a little more. So the bottom here, x squared minus 1 squared, is the same thing as x squared minus 1 times x squared minus 1, right? And so if you FOIL all this out, you get x squared times x squared, that's x to the 4th, and you get a pair of negative x squareds, because x squared times negative 1 is negative x squared, and negative 1 times x squared is also negative x squared. So when you combine those, you get negative 2x squared and then plus 1. So now we have 1 over the square root of 1 minus that entire quantity. And then also, so we get 1 minus the thing we just found. And notice the parentheses here are really important, because that minus sign has to distribute to every term. And then the derivative of this is just 2x. So we're now multiplying by 2x, but I'll say 2x over 1, so that it makes sense how we multiply these now. So we multiply the numerators and just get 2x on top, and then 1 times anything is itself. And now let's just distribute this minus sign. So it'll be the square root of 1 minus x to the 4th plus 2x squared minus 1. And then this 1 and that minus 1 cancel. So we get 2x over the square root of 2x squared minus x to the 4th. Okay. So this would be the derivative. There's a little more simplifying that we could do, but let's just stick with this for now. So hopefully it makes sense why we use the chain rule first off, and then how it was applied. And if it doesn't make sense, please make sure to ask me in class. Okay, and then in a similar fashion, the other two really important inverse trig functions are cosine inverse and tangent inverse. So cosine inverse, or also known as arc cosine, it has domain also negative 1 to 1, and it has range 0 to pi actually. So that's one small difference. And if you think about why, notice that between 0 and pi, the cosine function hits every value that it normally does. It starts at negative 1, hits every number until negative 1, sorry. And it's also 1 to 1 here. It also passes the horizontal line test. And so its inverse is very nicely defined on this domain, meaning this will be the range of the inverse function. Okay? And then now if we think about what tangent looks like for one period, remember it has asymptotes at negative pi over 2 and positive pi over 2, and it looks like this. Notice that again, on this domain, it passes the horizontal line test. It hits all of the numbers it normally does, negative infinity all the way up to positive infinity, and so this is the perfect domain to define the inverse tangent function. So notice here, so we're going to say domain tangent x, we're going to just only consider it from negative pi over 2 to positive pi over 2. Parentheses here, because we do not want to include those points. The function doesn't exist at these 2 points. And the range, in this case, is all real numbers, negative infinity to positive infinity. So for the inverse function, these will flip-flop. So then, put like bullets here. So then tangent inverse, or also known as arctangent or arctan, this has domain negative infinity to infinity, the range of the old one, and the range is going to be the original function's domain. So these are just general things that are good to know about these functions. And of course, they satisfy the same properties that any function and their inverse satisfies. And if we do a similar process to what we did with sine, you can get the derivative of the inverse cosine function. So the inverse cosine function, its derivative is actually negative 1 over the square root of 1 minus x squared. And again, this will be defined for these values of x. And then the derivative of the inverse tangent function is just 1 over 1 plus x squared. And now notice you can stick any number into here. I mean, we had already said that the domain was all real numbers. And this is making sense too, because now I can stick any number into here for any x for any real number. So this is true for any real number x. So now we have the derivatives of these functions as well. So yes, now we've established the derivative of the more useful inverse trig functions: sine inverse, cosine inverse, tangent inverse. The other trig functions are used, inverse trig functions are not used as much, and their derivatives are listed in the book, so you guys can look that up, but they're not as frequently used. So let's just see some examples with functions that we do have. Okay, and let's see from the book. So one thing that we didn't do is sine inverse and cosine inverse, their graphs are somewhat boring because they're very short. They don't have a very big domain, right? Just negative 1 to 1. And so they're not very interesting. But we might as well think about what they look like. But so let's say domain. And then the range. Okay. And then to get what the inverse function looks like, it doesn't take too much work, because remember, to get the inverse function's ordered pairs, you just flip the original function's ordered pairs. So between negative pi over 2 and positive pi over 2, let's pick like a few more points. So let's say negative pi over 4, positive pi over 4, and then 0. So let's use these 5 points. So at negative pi over 2, we're at negative 1. At this coordinate, we're at negative root 2 over 2, which is a slightly less negative number. And then at 0, we hit 0. And now we're at root 2 over 2. And then at pi over 2, we hit 1. So the graph of sine looks something like this in that domain. Now, let's write these ordered pairs down. So, negative pi over 2, negative 1. Negative pi over 4, this guy, 0, 0. And then pi over 4 is root 2 over 2. Pi over 2 or 1. So for the inverse function, we will literally flip-flop all of these coordinates. So we just exchange them. So now we have negative 1, negative pi over 2. Negative root 2 over 2, negative pi over 4. And this is like 0.7 roughly, so negative 0.7. This one stays the same. And then these basically mirror the first two, except the minus signs aren't there. Okay, so these are the ordered pairs of the inverse function. So the way that sine inverse looks like is now the inputs, they'll go between negative 1 and 1. So let's just put the ones that we have. And then the outputs on the y-axis will be between negative pi over 2 and pi over 2. So I'll put negative pi over 2 here, negative pi over 4, there's 0, and then pi over 2. And then we just plot these points basically and fill the rest in. So we have that, and then this one, and then this is the same, this point, and then that. So it looks something like this. Basically what sine inverse looks like. So this is the graph sine inverse x. So yeah, very like I said, its domain is just between negative 1 and 1, so there's not much interesting stuff going on. So it's a very little small branch, and you've probably seen this before. And then if you do a similar process, you can also get the graph of cosine inverse, which again doesn't look too amazing. It just looks like this. So again, we considered cosine between 0 and pi. So we'll take 0 as 1 point, then we'll do pi over 4, then pi over 2, 3 pi over 4, and then pi. So we'll pick these 5 points. So at 0, it's at 1, and then root 2 over 2 here, and then 0, negative root 2 over 2, and then down here it's at negative 1. So it'll look like this. So this is what cosine looked like. And again, what were the ordered pairs? So at 0 it's at 1, at pi over 4, root 2 over 2, pi over 2 it's 0, 3 pi over 4 it's negative root 2 over 2, and at pi it's negative 1. So again, we're going to just flip-flop these to get the graph of cosine inverse. So again, on the x-axis, so the x-axis will, now be constituted by these numbers, which again range between negative 1 and 1. And then the y-axis will range between these numbers, which are always just positive. So it'll just go from 0 all the way up to pi. So 0, pi over 4, pi over 2. Running out of space. Let me space out slightly bigger. So pi over 4, pi over 2, 3 pi over 4, and pi. Okay, and then now we just plot what we have. So the ordered pair here, instead of being 0, 1, it's 1, 0. So 1 unit to the right, and then we don't go anywhere. So 1, 0. And then this one will be root 2 over 2, pi over 4. So this many units to the right up here. And then 0, pi over 2. So stay here and then go up pi over 2. Negative root 2 over 2. 3 pi over 4. So left that many units up here. And last but not least will be there. So then this guy looks like this. And then it should always, this should be slightly higher up so that the bend, we want it to bend like this actually. So this point should be right there. Yeah, there we go. So the pi over 4, roughly it should look like this. So this is roughly what cosine inverse x looks like. And of course, you could always just like look this up on the internet, but to get a prettier graph, but my goal is to show you where the graph comes from. The drawing, of course, you know, I can't be as good as a computer, but this is the rough idea. And then last but not least, the more interesting graph is tangent inverse. Because now this one goes on forever. So if you think about tangent, like we were saying, here's negative pi over 2. Here's positive pi over 2. Now let's pick an intermediate point, negative pi over 4, positive pi over 4, and then 0. And remember that at negative pi over 4, tangent is negative 1. At 0, it's 0. At pi over 4, it's 1. And then negative infinity, this asymptote, positive infinity there. So it looked like this. And it goes on forever. So what are like the 5 ordered pairs? It's like negative pi over 2 corresponds to negative infinity. Negative pi over 4 was negative 1. 0 was 0. Pi over 4 was positive 1. And pi over 2, infinity. So these are kind of like the ordered pairs in this case. Of course, this having infinity as your y-coordinate doesn't make perfect sense, but we get what we mean in this case. Okay. So we have that. So then, yes, if we flip these coordinates now, we get negative infinity, negative pi over 2, negative 1. This one's unchanged. So we get that. And so notice that the x-axis values go from negative infinity to positive infinity, but the y-axis values are trapped between pi over 2 and negative pi over 2, which we already knew this because we knew the domain and range, but this is just another way of seeing that. So instead of having the asymptotes be vertical, they're horizontal now. So you have one horizontal asymptote at pi over 2 and another one at negative pi over 2. And then, at 0 we're 0. At -1 we're negative pi over 4. And +1 we're positive pi over 4. And then we approach infinity. As we approach infinity, we get close to this. As we approach negative infinity, we get close to that. So the graph looks something like this. Maybe put this slightly higher. So maybe put pi over 4 up here. Okay, so this guy goes on forever. So notice it's basically very similar to the graph. Oh, forgot a minus sign here. It's very similar to the graph of tangent. It's just kind of been rotated, right? If you rotate this clockwise, then we will get the original graph of tangent. Essentially, you'd have to reflect it again, but it's like a rotation and reflection and so on, but you can kind of see why the vertical asymptotes turn into horizontal ones, and now it has this behavior. So this is pretty neat, and we can summarize the behavior at the asymptotes like with these results. So, and this is tangent inverse. So the limit as x goes to infinity of tangent inverse is pi over 2. That's one result. And the limit as x goes to negative infinity, tangent inverse is negative pi over 2. So these are two really cool results about the inverse tangent function. And yes, these things will pop up a lot throughout the rest of this course, these limits here. And basically, hopefully they make sense once you see the graph. So now let's do one more example with the derivatives, and then we'll see how these new derivatives that we found will help us find the integral of certain functions. Because remember, every time we have a derivative, we in a sense now know the integral of some function. And hope that'll make more sense here in a second. So let's say we want to find the derivative of this guy. So it's the reciprocal of sine inverse, meaning that this, another way of writing it, is sine inverse x, all raised to the -1. Now, if this -1 here is confusing you, and it's just notation, you can just think of this as arc sine x, this function raised to the -1. Now there's not two -1s floating around. Here the -1 is an algebraic, it has algebraic meaning. It means take the reciprocal. In this case, it's just notation, but hopefully, if that still is confusing, you can think of it just as arc sine. So then if you want to take the derivative, you would use the power rule in conjunction with the rules that we just learned for the derivative of sine inverse and the chain rule, because we have something raised to the -1 power. So that's the power rule. So we cover this up, and then what does the power rule say? It says bring this guy out in front. So -1 is just a minus sign. And then the thing I covered up, you take -1 minus 1, which will essentially be -2. right? That's from the power rule. If you had x to the negative 1, its derivative is negative x to the minus 2. And in this case, x is all of that. But because this is not just x, the price you pay, again with the chain rule, is you multiply this by the derivative of the thing you covered up. Okay? So then this becomes, another way of rewriting this now is negative 1 divided by sine inverse x squared, right? Minus 2 means take the reciprocal and then make the power positive. And then this derivative we know is 1 over the square root of 1 minus x squared. Okay, which we can combine to get an overall minus 1 over sine inverse x squared times this. Which that's a pretty weird looking function, that's for sure. But that will be the derivative of this guy. Okay, and then let's do one more example. Let's say you do y is x tangent inverse or arctan root x. Okay. So now here, the first step is to use the product rule because we have a product of two functions, x and arctangent. So step 1 is use the product rule, which says you take the derivative of the first function, like this is like f, you can think of that as f, and this is like g. So remember, it was f prime times g, so x prime times just arctangent root x, plus now g prime, the derivative of g, times just f. Okay. Now this is just 1, so we get arctan root x. And then to take this derivative, we need to use the chain rule. Because remember, we said that the derivative of arctan just x is 1 over 1 plus x squared. So in this case, we don't have x, we have square root of x. So we have to use the chain rule. So the chain rule says it'll still be 1 over 1 plus whatever this is, root x squared. So as opposed to being x, it's a root x squared. But then we have to multiply by the derivative of root x, the thing that we covered up essentially. And then this x was just floating out in front the whole time. So times that x. So now I have arctan root x plus, so the order that we multiply these numbers doesn't matter. And you can think of this x as x over 1. So this x over 1 times this gives you an x over 1 plus x, right? Because when you take root x and you square it, you just get x. And then the derivative of root x, remember, is the same as the derivative of x to the 1/2, which by the power rule is 1/2 x to the minus 1/2. But another way of writing that is 1/2 times 1 over x to the positive 1/2, which is 1 over 2 root x. As this is the way that we will write it. So we'll multiply this by 1 over 2 root x. Okay. So then this x over this root x will essentially give you a root x in the numerator. So then we get arctan root x plus root x, and then this 2 remaining will multiply the 1 plus x, the whole quantity. And that'll be the final answer. Okay, sweet. So then, if you recall, because we have derivative formulas, the 3 important ones, remember the other 3 inverse trig functions, secant inverse, cosecant inverse, and cotangent inverse, they're not as used as often, so their derivatives exist and they're in the book, but we're going to focus on the main 3. Because we know these 3 rules, and let me make sure that I didn't miss anything here. This is 1 minus x squared as well. Okay, because we have these 3, remember, this tells us integration formulas as well. Because if we take the integral of both sides of these 3 different equations, remember that it cancels out here. So the integral and then the derivative, they just cancel out to just give us sine inverse. And then this integral still floats around, so now we know this really interesting property is now that the integral of 1 over the square root of 1 minus x squared dx is sine inverse x plus c. So that's a new integral formula. And that's what I meant by if you know the derivative of one thing, then now you kind of get a new integral formula. Because the derivative of sine inverse was this guy, we get that. And similarly, we get these 2 more results. So we get the integral of -1 get that. And also this one. Of which these 2 boxed in red are particularly important. They show up pretty frequently. I mean, you can just see the difference between these 2 is the minus sign. So it's not too huge of a difference, but those 2 show up pretty often. And then let's do an example so you can see what I mean. So let's say you want to find integral from 0 to 1/4 of 1 over the square root of 1 minus 4x squared. Say you want to find that. Okay. So you might be like, dang, I have no idea how to do this. This looks pretty weird. Like, where are you going with this? So notice that what you can do is you can think about this guy, because the idea here is we have 1 minus something squared, but it's not the whole expression squared, right? This says the x, whatever that expression is, that whole thing is squared. So you can think of this as the square root of 1 minus 2x squared. So now this whole expression, when you square it, you do get that back. That's why they're equal. And now that's perfect. This looks like this exact form here. So this will become just sine inverse of not x, but 2x. All right, because this wasn't x squared, it was 2x squared. So this sine inverse of 2x evaluated from 0 to 1/4, which is going to be the sine inverse of 2 times a fourth minus the sine inverse of 2 times 0. Okay, which this is 1/2 here. This is 0. And then remember, how do we figure out what each of these were? This is the angle between negative pi over 2 and positive pi over 2, such that sine of this angle needs to be equal to 1/2. And remember, this angle has to be in the range of our function. So it has to be between these two. And then, I think we already did this one, it's pi over 6, right? Or 30 degrees. So this is pi over 6 minus, and then to find this one, you ask yourself, sine of what angle theta is 0? Well, that's 0, because sine of 0 is equal to 0. So this is pi over 6 minus 0, which gives us the grand final answer of pi over 6. So that's pretty cool, because normally we would not, no technique we have developed would allow us to find this integral. U substitution would be hopeless as well. So this is nice that we have that. And then let me see how much time we have. Okay, so instead of deriving this formula, I'll just give you the final product. Or we could think about the derivation maybe in class. Is if you have the integral of 1 over x squared plus a squared, notice it's very similar to this. In this case, or let me write it, a squared plus x squared. Notice a, if you let a be 1, we get this. So it should be really similar to tangent inverse, but a slight modification. And it turns out that it's just going to end up being 1 over a tangent inverse of x over a plus c. So that's the slight modification that we get. So instead of being tangent inverse of x, it's 1 over a tangent inverse of x divided by a plus c. And you can see when a is 1, we get this back. So it makes sense. So this is another formula that's going to occur pretty often. You could say that. And so let's do an example of that. And yeah, if we have enough time, I'll go through the derivation of this. So let's say we want to find the integral of x over x to the 4th plus 9 dx. Okay. So now you might be like, hey, this is an x to the 4th, it's not an x squared. So again, we're going to use this little trick, is we're going to think about this guy as x squared squared, and then 9 we'll think of as 3 squared. So this is like my a here, and this is like x. I'll put it in parentheses because it's not really x, it's like x squared, but hopefully this makes sense. Okay, but now there's still this pesky problem of this x here, because to use this property, we need a 1 in the numerator. There can't be an x up here. There can only, if there's a constant, that's fine. You can pull the constant out front. So now we have to combine this with our favorite and only technique of integration that we know is U substitution. So what we're going to do is we want to turn this expression into just like something squared. As opposed to it being x squared, we want it to be like u squared. Because then as long as this is u squared and the variable here is du, that's fine. So this is dx. So what we're going to do is you'll let u be x squared, and then that would mean that du is 2x. That would mean that du is 2x dx, sorry. Du over 2x is dx. Okay, so that's really good now, because now our integral here will transform into x over u squared, right? This becomes u, so u squared, and then plus 3 squared. That's still 9, that doesn't change. But now dx becomes du over 2x, and look at that, the x cancels out. So that x cancels out. And we'll be able to pull this du divided by 2 as a 1/2 floating out in front of all of this. So this will now be 1/2 integral of 1 over u squared plus 3 squared du. Which this is really nice because now we can use this formula that we have. So the 1/2 is floating out in front, so we get 1/2 times our answer, or yes, it's not a quantity, so it's just 1/2 times one thing. So it'll be 1/2 times 1 over a, which is 3, so times 1 over 3, tangent inverse of u over 3, and then plus c. And then now we substitute back for u. So 1/2 times 1/3 is 1/6, tangent inverse of x squared over 3 plus c. And that's the final answer. So that's pretty neat. We just used a lot of the stuff that we've been learning all in one go. U substitution, integrals, the derivative or the integral of inverse trig functions. All of this is coming together. So this was a really good example of how things are starting to build upon themselves. Okay, and then I'm trying to see if it's worth it to do one more example. Definitely is. Have a little bit more time. Yes, let's just do one more example from the set of homework problems. And let's do an integral because I guess those are fun, or some, maybe fun. So this one is number 61. It has limits of integration, but I won't go there. We'll just stick with indefinite integral. So it's the integral of sine inverse x over this. Yes, that's it. Okay. And then if if you sit here and stare at this for long enough, you can see that u substitution might be helpful. So what we do is we're going to let u be sine inverse x. So then du is the derivative of this, which is this guy, times dx. And then now, if we want to isolate dx, we would just multiply both sides by this, the square root of 1 minus x squared. So we get root 1 minus x squared, du is actually dx. Now this is perfect, because now we have sine inverse x, that's u, this guy floating out from the beginning, but now dx gets swapped with this, which is really nice because look what cancels. So now we just have the integral of u du, which is 1/2 u squared plus c, which is 1/2 sine inverse x, that thing squared plus c is the final answer. Okay, and then we still have a little bit more time, so maybe one more example. Oh, this one's a really nice one. This is number 63. Okay. So what we're going to do is we're going to first do some algebra and see that you can rewrite this as, you can take this quantity and divide it into each term. So this will be 1 over 1 plus x squared plus x over 1 plus x squared. Right? If you add these two fractions back, you'll literally get this. So we can split them apart. Okay. And then we can write these as two separate integrals. Which this one we already know what it should be. This is tangent inverse x. So that integral we know. And then this one, let's think about for a second. Had this just been a 1 here again, it would be tangent inverse, but this x is ruining things. But if you just do u substitution here, you can see how that x will go away. So what we're going to do is we're going to let u be equal to 1 plus x squared. Okay? And then because of that, du will be 2x dx. And then so du divided by 2x is dx. And you can see how this x will cancel out with what we have. So now bringing this here, this is tan inverse x plus the integral of x all over u du over 2x. Now these x's cancel out. So this is like a 1 here. And then remember this du divided by 2, you can really just think about it as a 1/2. So we really have 1/2 integral of 1 over u du. And what was the integral of 1 over something? Remember, it was the ln of the absolute value of it. So this now becomes tangent inverse x plus 1/2 ln absolute value of u plus c. And then when we substitute back, it's now tangent inverse x plus ln absolute value of 1 plus x squared. Oh, sorry, I forgot the 1/2. But now if you think about it, 1 plus x squared is always a positive number, right? X squared is always positive, and if you add 1 to it, it's still going to be positive. So we can actually drop the absolute value symbol here. Just put that. And this will be the final answer. So this one was really nice. Used a lot of different stuff that we've talked about. And you can see that this looks pretty dang complicated, but remember, if you take the derivative of this, you should end up back with this or that. They're the same thing. But you should end up back to the original function that you had. Okay, very cool. Alright, so I think we are out of time, and I'll see you guys next time.